So Federico asked me to fill in today. So last time he told me he was triangulating the n-gon. And the point was that there was a complete answer there. We know how many triangulations there are, what they are, and it's a nice number. Anybody remember? It was the Catalan number. So I want to do another example, maybe the only other family, certainly the only other one I know, where we can get a complete answer, and that's the d-dimensional cross-polytope. And I'm going to denote it CD delta, the way Ziegler's been doing. That is, it's the dual to the d-dimensional cube CD. So, for example, if I start with the two-dimensional cube, then there are two ways I can triangulate it. Right? I need to break it up into triangles. I don't want to introduce any new vertices. So these are my two choices. Well, I could try to draw the ones of the octahedron, but I'm just going to jump to some facts in general. So CD delta is the convex hull of 2D points, and these are plus and minus E1 through plus and minus ED. And I want to first ask, what simplices can I possibly use in a triangulation? Well, for simplex, I need d plus 1 vertices. So by the pigeonhole principle, I'm going to have EI and E minus I for some I. But on the other hand, if I take plus and minus EI and plus or minus EJ in the same simplex, well, these are 4 points that all lie in a plane. But that's bad because we don't want 4 points in the same plane. That's not the way simplices behave. Every 3 points in a simplex form a triangle. Every 3 vertices in a simplex form a triangle. In fact, every d points form a d-dimensional simplex. So the conclusion is I'm going to have to take EI and minus EI and then well, I can't take ej and minus ej, so I'm going to have to take 1 from each remaining pair. So I'm going to take either e1 or minus e1, e2 or minus e2, and so on for every coordinate except the ith. And by symmetry, I can make any of these choices. I choose a value I, choose a sign for each of these remaining things, and all of those are going to work. So I have n choices for I, or sorry, d choices for I. Whoops, n should be d here. And then for each other coordinate, I have 2 choices. So I have 2 to the d minus 1 choices for my signs. So there are d times 2 to the d minus 1 simplices I can use in a triangulation. So in fact, let's introduce some notation. Let's say vector epsilon is epsilon 1, epsilon 2, epsilon I minus 1, epsilon I plus 1, epsilon d, and these are all either plus or minus 1. So I'm choosing my signs here. I'm going to denote t sub I super epsilon to be the simplex that takes exactly this choice. I'm going to take ei. Let's actually write it in order. So I'm going to take epsilon 1 e1, epsilon 2 e2, epsilon I minus 1 ei minus 1. Then I'm going to take both ei and minus ei, and epsilon d ed. So this is what my candidate simplices look like. Does this notation make sense? And I'm going to call I the type of ti epsilon. So here's the lemma, lemma 1. If I take a triangulation, I have to choose a bunch of these simplices. My claim is that all of the simplices I use must be of the same type. So here's the proof. Suppose not. Well, if I take, if T1 is of type I, and T2 is of type J, different from I, then T1 is going to have an edge that looks like from EI to minus EI. Every pair of vertices forms an edge. And similarly here, but now take the intersection of these two edges. Actually, instead of making these sets, let's make them intervals, because that's what they are. What's the intersection of these two edges? It's the origin, exactly. But that's no good, because the origin isn't a face in the tetrahedron. It's not a face in any of these things. Remember, in a triangulation, I intersect any two faces. I'm supposed to get a face of each one. So that proves the lemma. OK, so then the second lemma. Now that I know I'm going to use type I, my claim is that I need all of them. OK, so here's the proof of that one. Let's choose an arbitrary sign pattern, epsilon. And, well, I'll choose I guess. I have to do that first. And I'm just going to write down a point which is only in one of these simplices. And here's the point. Let's just take epsilon 1, epsilon 2, epsilon I minus 1, 0. Zero in the ith place. If you think about which of these simplices it's in, this is going to lie in Ci epsilon, but not in Ci delta for any other delta. I guess there's something to check, but I'm not going to write that out. Well, but what have I now shown? I've shown that I have to use simplices of the same type, and the only hope is to use all of them. So there are only d possible triangulations. So it's exactly take all of the ones of type I for some I. So there aren't very many triangulations. There are at most d of them. Good so far? Well, I claim that these actually are triangulations. So I guess I'll call this a theorem. So what do I need to do? I need to show two things. So I guess when I did limit 2 here, I showed that I need all of them. I didn't show that the union of all of them actually is the whole simplex. but it is. So let me show that. So the first thing I need to show the union over epsilon of Ti epsilon actually is the whole thing. And second, I need to show that the intersection of any two of these guys actually is a phase. So for the first one, I basically just do kind of the reverse of that. So let's take an arbitrary point in CD plus 1. Then what I'm going to do is, of course, just choose epsilon I to be the sign of xi. Or epsilon j, sorry, to be the sign of xj for each j which doesn't equal I. So now I want to show that x1 through xd is in this simplex Ti epsilon. So that means I need to write it as a convex combination of the appropriate things. So, well, how can I break down xi in this way? Well, clearly I have to take this as the sign, and that is the magnitude. And for the ith coordinate, well, so the ith coordinate is the only one where I don't know the sign. But that's OK, because I have both E I and E minus I in my choice of vectors. They're both vertices in this simplex. So I'll just say, OK, whichever it is, take the sign of, no. Just take the sign of xi times absolute xi. Let's see. Oh, and why is this actually a convex combination? Ooh. So the reason ought to be that if it weren't, the point just wouldn't have been in the octahedron, or rather the in the crosspolytope to begin with. Anybody see how to do that? I mean, geometrically, it's kind of clear, right? I mean, you sort of think about dividing the hypersimplex into orthents. And say if the jth coordinate is positive, it's kind of silly to use minus ej when I write this as a point in the simplex to begin with. But I'm sorry, I think I may have to pass on this for the moment. I'm just going to get into a notational mess. So I'll leave the exercise. This is actually a convex combination. You guys see what I'm trying to do at least? Okay, I think that's the important thing. I think once you realize this, and we sit down for a few minutes, you'll see how to do it. Okay, so the second thing I need to show is that if I intersect two of these, I get a common face. Well, what are the faces of Ti epsilon? I guess I have to ask that first. Let's say, what are the facets of Ti epsilon? Well, it's exactly what I was just saying. The point is that we're in the cross-polytope, but we have to be in the right orthant. So the inequalities that I need to introduce are exactly the ones that tell me I'm in that orthant. So these are going to be exactly that xj is greater than or equal to 0 if epsilon j is 1. Xj is less than or equal to 0 if epsilon j equals minus 1. And xi just needs to be between minus 1 and 1. So, okay, so what's the intersection of Ti epsilon and Ti delta? Well, if the signs are different, suppose epsilon j doesn't equal delta j. Then what do we know about the jth coordinate of any point that's in both of these simplices? It has to be 0, right? Because to be in, if epsilon j is plus 1, that's saying the jth coordinate better be positive, or at least non-negative. And if delta j is minus 1, that means the jth coordinate had better be non-positive. So the constraint is going to be exactly that xj equals 0 in that case. And if, and otherwise we don't get any new constraints. Well, okay, no, I guess we just get that it's greater than or equal to 0. If they're both 1. negative if they're both minus 1, or anything if j equals I. So there's no constraint when j equals I. Okay, but the point is that these are exactly the facets I wrote down. So the constraints I have are, in fact, facet inequalities. Therefore, it's an intersection of facets, hence a common face. I know what the problem is. What's bothering me is that this is not the right constraint. This is true, but it's not strong enough. Right? That would give me, what I need to say is that the sum of the coordinates is actually between minus 1 and 1. Otherwise, we might not be in the cross polytope. Let's correct this. But the point is, the new inequalities, xj, or new equations rather, xj equals 0, are facet equations of both simplices. So that is Ti epsilon intersect Ti delta is an intersection of certain facets of Ti epsilon, hence a face. I want to do this in some detail. And if it isn't clear, we should think about it later, check with Federico, because I think there's going to be a homework problem where you have to show that something else is a triangulation. So you're going to have to do this kind of thing. Check that you really, when you intersect two simplices, you really get a common face. I mean, what is this doing? I mean, the point is otherwise, you can say, well, we have a bunch of things that maybe add up to the cross polytope. Maybe they intersect in some crazy way. And that's not what we want. Triangulations are supposed to be very nice. We're breaking it up, and we're not introducing a bunch of new intersections and faces in the interior. OK, so this modulo, a couple details, proves that I really have a triangulation. So there are exactly d triangulations of the d cross polytope. Why is this a regular triangulation? Or is it a regular triangulation? Well, so yes, of course. And one reason is that I think Federico showed last week that every polytope has a regular triangulation. But of these d things, of these d triangulations, they're all related by symmetries of the cross polytope. Cross polytope has lots of symmetries. Certainly, I can permute coordinates so as to turn one of these triangulations into another. But that means that either all of them are regular or none of them are. So they're all related by symmetry. So they're all regular. So the symmetry here would just be to, say, switch the ith and jth coordinate. Well, okay, but that's kind of cheating. So here's what you really do. Suppose I wanted to do it for the square. And I want to say, okay, I have this triangulation. How do I make sure it's regular? Well, the point is I want to make sure that I see this diagonal and not this other diagonal. So how about if I just make these 2 points low and make these 2 points higher? If I do the heights in red, let's say 0 here and 1 there. And so now this whole edge here is going to be at height 0, and this other diagonal, the one I don't want, is going to be at height 1. So I make sure that I see the right diagonal. Remember this idea of lower hull and lifting? OK. And so in fact, this works in general. Because the point is that what's the key factor about the ith triangulation of the D I gave? Just like here, the point is that there's one special edge that goes through the middle of the thing. You know what I should have done? I should have drawn this as a diamond rather than a square, because that would make it generalize better. So say I want the one where I want to pick out the edge from minus E2 to E2. Then I take the height of E2 to be 0, height of minus E2 to be 0, and the height of the other points to be 1. So let's just generalize that. If I want to do this, if I want to get this triangulation of the d-dimensional thing, take heights, height of EI equals height of minus EI equals 0. And heights of all the other vertices to be 1. So the idea is the same. So this diagonal, or rather this edge, from minus EI to EI is going to appear. It's in the lower hull. And so we're going to see exactly the simplices that have this as an edge. And those are just the ones I want. So this doesn't look very generic, right? I took a whole bunch of things to the same height. But it turns out there's just so few choices I need to make. There's so few possible triangulations that this is all I need to do. Questions? So with a few minutes left, I want to just say something about a contrast. So triangulating the cross-polytope was easy. There are very few triangulations. And modulo a few details, we pretty much proved what they were. Let's do the cube. Cube is just the dual of the cross-polytope. Well, it turns out that in that case, we have no idea what all the candidates are or how many there are. Well, we have some idea, yeah. Yeah, OK, so I guess what I meant is the asymptotics. Right, people have certainly done this in low dimensions. It's an important thing. You can compute them. So let's say very little known for large d. So one problem is that we don't even know how many simplices to use in a triangulation. Well, the maximum number what's the smallest volume a simplex could have? It's going to be a simplex whose coordinates are integers, 0, 1 vectors. And those are going to have volume 1 over d factorial. So for example, let's take the simplex where I just take the points 0, E1, E2, ED. So if I take the convex hull of that, so specifically, it's going to be the determinant of the matrix E1. It's 1 over d factorial times the determinant. So as long as you have 0 as one of your vertices, you can compute the volume this way. Have you guys seen this fact? Oh, OK. Well, this is a great thing to know about. So maybe this should be another lecture sometime. And why is this? The point is, this is a general thing. If we take 0, I can always get the volume this way. And if I don't take 0, I just take the differences from the ith vector to the 0th vector as the columns of my matrix. So let me write that down.
This is a really nice corollary that any polytope with rational coefficients on the, rational coordinates has a rational volume.
Yeah. Very nice. If I had more time, I'd explain why that's true. Maybe you can explain it.
Well, I mean, once you have that formula.
And then you use the fact that there exists a triangulation, right? I guess that's the key step. Then each of those simplices, you compute the volume using this formula. It's going to be rational. Add them up, and you get a rational number. OK, yeah, so that's great. OK, so if any simplex I use has volume at least 1 over d factorial, in fact, an integer multiple of d factorial, then the most simplices I could possibly use is d factorial of them, because the cube has volume 1. And in fact, you can do it. So let me give a reference, the place I looked this up, which is amusingly called Like what we know about the cube, what is known about unit cubes. By C. Zong. This is always possible. You can always use the maximum possible number. So what isn't known as the min? What's the minimum number of simplices you can use? So let me do an example, at least in 3 dimensions, where you don't use the maximum number. Let's say this is 0. And let's take 2 opposite pairs of vertices, like 0, 0, 0, actually not opposite, but across faces. 0, 0, 0, 1, 1, 0, 0, 1, 1, and 1, 1, 0. And let's just take the simplex that's the convex hull of those 4. Well, so what happens here, maybe this is hard to see in the picture, is if you take this simplex, what's left is 4 simplices around each of the remaining vertices. So if I look around this vertex, and I see what I've got, or what I can take, there's only one choice. And similarly around here, and around here, and around there. So if I take this simplex and those 4 others, I claim that's a triangulation. So this would only have 5 simplices. And why is that? Well, this one I wrote down. So it's going to be 1 over 3 factorial times the determinant of this simplex. So that's 0, 1, 1, 1, 1, 0, 1, 1, 0, whoops, 1, 0, 1. This determinant is 2, so this has a volume of 1/3. And the other simplices all have volume of 1/6. So there's a choice. I can triangulate the cube with 6 simplices, or I can triangulate it with 5 simplices. And so there's, in general, what are the choices? And so according to this paper, just when it was written, the best thing that was known, so let tau sub d equals the minimum number simplices in a triangulation of the d cube what's known is that 2 to the d times d factorial over d plus 1 to the d plus 1 is less than or equal to tau d is less than or equal to 0.816 to the d times d factorial. So that's a lot to unwind. And maybe it's not even obvious that this number is less than that one. But it is. And remember that, and think about this. So So they both have a d factorial in here somewhere. So remember that the maximum number we can use is just d factorial. And so then so the question is essentially, how much bigger can I make the simplices? So, and then dividing by that number, how much smaller is the number I need to use? What fraction, here's a better way, what fraction of d factorial is the minimal number of simplices I need to triangulate the d cube? And of course, there are also a bunch of numbers known for small d. People have computed this exactly. So it's also known, whoops. Tau 1 is 1. Tau 2 is 2. Tau 3 is 5. That's the one we just did, so I can't triangulate the cube with just 4 simplices. Tau 4 is 16. Tau 5 is 57. Tau 6 is 308. And tau 7 is 1493. Okay, so the lesson is that there are a lot more choices, and it's much more complicated to triangulate a cube than to triangulate a cross-polytope. Let's stop there. Questions? Where does what? The 1/6? Oh, so that's 1 over d factorial. And I think if you want to actually prove this, you probably do it by induction. So the volume of a, let's see, well, a one-dimensional simplex, the unit simplex would be 1. The area of a triangle well, of course, you know this is a half. But suppose you want to do this. How would you show this? And how would you show this in general for an n-dimensional thing? Well, I could integrate, right? That sounds kind of silly, but I say, OK, the base is a one-dimensional triangle. I know what its area is, and the height is 1. And then how do I figure out the area of the tetrahedron? Maybe there's a better way to do this. I don't know. But this is the one I thought of. You do the same thing. The base is a d minus 1-dimensional simplex. The height is 1. You integrate, and you find that its volume is a 1/6. And I think if you write this out in general, you're going to get that each time you do it, you're going to divide by d. Hence, the answer is 1 over d factorial. And yeah, I guess I shouldn't mention integrals in a discrete math class if I can avoid it, but I don't know another way.